Today we're going to carry on looking at two-variable statistics. In particular, we're going to look at something called linear regression. Regression is an analytical technique for determining the relationship between a dependent variable and an independent variable. Picture your scatter plots, x-axis independent, dependent is on the y-axis. We're used to that, right? When the two variables have a linear correlation, you can develop a simple mathematical model of the relation between the two variables by finding a line of best fit. In other words, you can come up with an equation to represent the line of best fit. Then you can use the equation of this line to make predictions by interpolation, which simply means estimating the values between data points, or extrapolation, which just means estimating, I see there's a typo here, estimating, beyond the range, not the range, of the data. Interpolation is always safer than extrapolation. It's always safer to estimate between data points than to extend it beyond, because you never know what's going to happen when you go beyond. But anyway, that's what those two terms mean. Let's just jump into a couple of examples. The first one, a university would like to construct a mathematical model to predict first-year marks for incoming students based on their achievement in grade 12. Well, that's a good idea. A comparison of these marks for a random sample of first-year students is shown below. I see 2, 4, 6, 8, 10 students there, 10 marks. Construct a scatter plot for these data. In the interest of saving time, I've already done that. Which variable should be placed on the vertical axis? On the vertical axis, it should be the first-year average. And the reason for that is because it is the dependent variable. Supposedly, what you get in first-year university is going to depend on how you did in grade 12. That's why we're always talking about things like learning stuff for the sake of learning it, not just to get the marks, so that you have knowledge and it's going to help you later on. But clearly, if one is going to depend on the other, first year would depend on grade 12, if for no other reason that in time it comes after the grade 12 one. Classify the linear correlation based on the scatter plot. So remember, we can look at a scatter plot and we should be able to get an idea of what's going on just from a glance. And to me, it's pretty clear. These are tightly grouped data. Even if the graph had been spread out more, there's still these dots are close together. In other words, we didn't have to have this grid that goes all the way down to 0. Even if we just cut it off at this part, you'd still make a good argument that these points are grouped closely together. And it's also pretty clear that they are going upwards from left to right. So we call that a positive, or let's call it a strong positive correlation. Remember the R values, we've talked about those before. I would estimate that is a fairly high positive R value. Estimate the line of best fit. Measure the slope and the y-intercept for this line. Write the equation for the line of best fit. Okay, so in order to do this, it's an estimate, right? So it's never going to be the exact same from one person to the next, but there certainly should have some similarities here. I'll try the best I can here on the iPad and see what I can come up with. Let's start up here. All right, that doesn't look terrible. I think maybe it's off a little bit. Maybe it's a little too steep. But as far as estimates go, it's not terrible. So if I want to get the slope, then what we do is we find a couple points that we can read on the line. So let's say this point right about here, which looks to be at about 75, 65. And this looks like another point that I can read fairly easily. Looks like it's about 50 and 35. Anyway, we'll just go back to our grade 9 idea and we'll draw a little triangle, and we'll see that from 50 to 75 is increasing by 25 here. From 35 up to 65 is going up by about 30. And so the slope is going to be rise over run. Let's zoom in. 30 over 25. Where's my calculator? 30 divided by 25 is 1.2. I should know that. Anyway, there we have a slope of 1.2. And the y-intercept, now this has gone down below the x-axis, so it looks like, if again, I'm just going to, this is just estimation here, it looks like about negative 25. It looks like it's about the same distance below as 25 was above. So we'll just, in the interest of saving time, we'll see. Let's do this in a different color. Just so it's, so negative 25, b equals negative 25. Put it together, what do we have? Y equals 1.2x minus 25. There is our equation for the line of best fit. Now we can make predictions with this. So we can say, okay, what if someone has a different first-year student had an 82 average? We want to predict what they're going to get when they go to university. Well, we stick that in for x. That's our x value. Y equals 1.2 times 82 minus 25. 73.4. That seems reasonable. We expect people's marks to drop when they get to university, or maybe even just 73%. That would be interpolation, by the way, because 82 would fall right in somewhere around here, right? So we're looking for a point right in about here, and that's right in the middle of the dot. So again, that's interpolation. The grade 12 student, someone was a grade 12, sorry, I'm just reading the question backwards. The grade 12 average for a student who had a first-year average of 60. They don't usually want to use it for this, but we could work backwards. So if I was at the university and I had a student who had a 60, then I could say, I can predict that maybe what their grade 12 average was. Now this is our y value, so I'd put 60 in here. 1.2x would be the grade 12 average. And then I can solve this. I can add 25 to both sides and divide by 1.2. I can predict that they probably had an average in high school of about 71%. That would be extrapolation, because none of the points, 71%, I guess actually it's not necessarily. We had a few that were lower than that, but it is definitely towards the left side of the dots, so it's getting down there. Anyway, we'll move on. Here are the slope and y-intercept of calculated using graphing software, which I'm going to show you to use tomorrow. I won't do it today, but I did calculate it, and I got a slope of 1.26 for this data and a y-intercept of negative 30, giving me an equation of y equals 1.26 x minus 30. Let's see if we can get these both on the screen together. So compare this to this. Remember, I just did my line of best fit. That's not terrible, right? I did a pretty good job, a decent job anyway, of comparing these two things. It's a bit thick there. So are they close? Yeah, they're close. Because a line of best fit is a decent estimate, as long as you can see the trend. We can see the trend going back to this data, to these scatter plot, these points. The trend is pretty easy to see. The points are close together. It's clearly going upwards. It's not very hard for me to draw a line of best fit. No E on the end. Clear trend. Okay, recalculate your predictions from part D using the new values from part E. So in other words, just use the new equation. So y equals 1.26 times, I think it was 82, minus 30. Let's see what we get now. $73.3. Compare that to what we had before, which was 73.4. Whoa, that's pretty good, eh? Very close. Let's compare it to, we put 60 in here, 1.26 times x minus 30. So again, we'll do 60 plus 30 divided by 1.26. And we get 71.4. And again, compare that. That's not bad. We're not always going to be this accurate, but I got a pretty good estimate on this one. And again, it's because the dots were close together and I could see the trend fairly easily. In fact, it is, as it says here, it's fairly easy to eyeball a good estimate of a line of best fit on a scatter plot when the linear correlation is strong, which it clearly is. However, an analytic method using least squares fit gives more accurate results, especially with weak correlations. So, in other words, imagine my scatter plot back here. What if it had been more something that looked like this? And the dots were more spread out. I could still estimate it's like this, but maybe it's more like this. Or, you know, it's easier to make mistakes and to not be as accurate when you don't have a strong correlation. Okay? Consider the residual or vertical deviation of each data point from the line of best fit. So that's what a residual is. A residual is a vertical deviation from each data point from the line of best fit. So look at this graph here, this picture of the graph. We got some dots here. We've got a line of best fit drawn in here. The residual is, if I take, say I take this point here, the residual is this distance between this point and the line of best fit. That's a pretty big residual on that one. Some of them are much smaller. This one's much closer to the line, and so this one's got a very small residual. So we take all these residuals, you know, they're either above or below the line of best fit, and in order to calculate the line of best fit, what we want to do is we want to minimize those residuals. We want to make those residuals the smallest as possible. Obviously, with a scatter plot, unless it's all perfect correlation, there's always going to be some residuals, because as long as some points aren't on the line, there's going to be a residual. So it's on the y value anyway. I'm just skimming through what the note says here. Same x coordinates. So basically what I just illustrated here. Notice that the residuals are positive for points above the line, and they're negative for points below the line. The Boses show the squares of the residuals. The boxes, that's what it should say. It should say the boxes show the squares of the residuals. So the boxes show the squares of the residuals. In other words, if we take, let's go back to this one here. I just leave that one there. So there's my residual. But if I make a box out of it and then give that same distance this way, we can calculate an area, of course, right? Let's say these units, let's say for argument's sake, this is a unit of 2. So we got 2 this way, we got 2 this way, the area equals 4. So we can calculate the square of the residual, get the area, and that will give us a measurement to work with. So the boxes, the bigger the box, you can get an idea that clearly this box here has a lot more area than this little one down here, which I can't even highlight with my Apple Pencil because it's so small. So increasing the residual, once we square it, magnifies that effect. So again, we want to get these as small as possible. So here's how we use this, put this together for the least squares method. For the line of best fit in the least squares method, the sum of the residuals is 0. So if we just add up the residuals themselves, they should equal 0. The positive and negatives need to cancel out. And the sum of the squares of the residual has the least possible value. Okay, so that's what we're looking for. Now, that's hard. I mean, for a person just to do that, to look at it, we can't do that. But we have formulas that'll help us with it. So here's the least squares formula. If we're putting things into y equals mx plus b form, or in this case, ax plus b is just what we call the slope, same thing though, then we have a formula for a, which looks a lot like our R-value formula. I think the numerator is exactly the same. The denominator, though, is a bit different. So it's not exactly the same as our R-value. And then we have, to calculate our b, our y-intercept, then we'd use this formula here. Y bar is just the average of the y's, x bar is just the average of the x's, and a comes from over what I've highlighted in green. So we have to calculate a first. But really what we're calculating here is the slope with this formula and the y-intercept with this formula. And we have to have the slope first so that we can plug it in here. Okay, let's look at an example using this. Applying the least squares formula. This table shows data for full-time employees at a small company. Let's just look at the data first of all. Age of the employee and their annual income in thousands. 33-year-olds making $33,000. 25-year-olds making $31,000. A jump ahead. 54-year-olds making $60,000. So it seems like the older someone is, the more they're making. Again, here's a scatter plot. I've already filled it in just to save some time. There's a very strong looking correlation there. I could draw a line of best fit. It would be, I'll just sketch and erase again. I mean, it's pretty obviously going to look something like that, like very strong, very high R value, clearly positive. We could estimate a line of best fit very easily. But we're going to use the least squares formula to do this. So what we want to do is we want to determine the equation of the line of best fit using this formula up here, these two formulae, A and B, and we'll start with A. So again, I've got a table here just to help us organize our values. So in this third column here, x squared, we're literally just squaring all the values in the first column. So 33 squared is 1,089, for example. So let's just fill this in. Okay, so there's all my x values squared. Then we have my y squared, which is just squaring everything in this column. So again, simple to do. It takes a minute to do it, but not mentally challenging in any way. Okay, so that's where those two columns come from. Let me just write out the formula again just so that we have it handy so you can see where everything fits in. So again, it's A is equal to N times sigma xy, so adding up x times y, minus sigma x times sigma y. All over n times sigma x squared minus sigma x squared. So again, the difference between this and this is where the squared sign is. In the first one, we're squaring the x's and then adding them together. In the second one, we're adding the x's together and then squaring it. So we don't get the exact same thing. Sorry, I just realized that I had filled everything in, but I was a bit misleading for a second. I mislabeled this column here. Just looking at the formula again, it reminded me that this is not actually, here, let's erase this. This is not actually y squared. This is x times y. My bad. So this last column was not y squared because looking at the formula, I just remembered I can see that we don't need y squared, but what we do need is xy. And the first one is still this number here is still 1089, but it's not from squaring the y as I was thinking. It's from doing 33 times 33. So it's the same. We still end up with 1089, but this next one here comes from doing 25 times 31. So my apologies. If you caught that, good on you. If not, don't worry about it, and let's move on. All right, so we got our x, y, and then we can add all those up. So we got these different values anyway, and at the bottom is sigma x. It's just adding all these things. So if we add the first column up, sigma x equals 292. If we add up all the y's, we get 329. If we add up all the x squareds, we get 11,712. And if we add up all the x times y's, we get 13,221. And now it's just a matter of putting everything in its appropriate spot. And by the way, there's 8 employees here, right? 1, 2, 3, 4, 5, 6, 7, 8. So n is equal to 8. So we have 8 times 13,221 minus 292 times 329 all over 8 times 11,712 minus 292 squared. Working that out, the numerator comes out to be 9,700. The denominator is 8,432, giving me an approximate value of 1.15. That's my A value. That's my slope. To do the B now, I can use this A. Remember, let's give myself a little room over here. So remember, to get B, that was y bar minus A times x bar. So we need to know y. We need to know the average of the A's, or of the y's, and the average of the x's. So in other words, we need to use this divided by 8 to get the average of the x's. Maybe we'll just do it down here. X bar equals 292 over 8, which gives me 36.5. And then I'm going to do the y's divided by n, and that'll give me my y bar, which gives me 41.125. So these are the two values that I will put in back up here. So 41.125 minus 1.15 times 36.5. That works out to be negative 0.85. That's my B value. So when we put it all together, we've got ourselves an equation. Y equals 1.15, x minus 0.85. Predict the income for a new employee who is 21 and an employee who's retiring at age 65. All right, so for this guy or girl, we have y equals 1.15 times 21 minus 0.85. And it's easy to use now that we've got it. So that means we would expect them to get $23,300 as their salary. For a 65-year-old employee, that works out to 73.9 or $73,900. So, comparing these two things, the least squares formula is more accurate. That is the kind of thing that's used way back here, like in example 1e, where I said I used graphing software. They use this formula to get an accurate equation. But I also saw that for something that's got a very strong correlation, an estimate can be good enough, right? My estimate was very close. So it depends. Is it worthwhile using the formula? Maybe not in this case. We get a really good ballpark just by drawing a line through these things, and, well, if your line's better than mine. But you get the idea. We get a very good ballpark just by drawing a line through this, and I could calculate the slope and the y-intercept a lot quicker without using the least squares formula. But again, it's not always going to be so easy to see. And tomorrow meaning next lesson, that is, we'll look at using software to do it. One last thing, though, before I'm done, and there's a bunch of writing here, but I'm just going to sort of hit the highlights, and I won't read it all to you, but just want to point out a couple things that we need to consider still. And that's how outliers affect two-variable data, because they do. So just, again, let's just sort of skim through this example really quickly. To evaluate the performance of one of its instructors, a driving school tabulates the number of hours of instruction and the driving test scores of its students. And it's shown in this table right here, right? So here's their data. What assumption is the management of the driving school making? So you got an instructor, and then you got the student scores on the on their test. So the assumption is that there is a correlation between instructional hours and test scores, and that it's an indication of the instructor's driving skills. Obviously, there should be some connection between them, but I would not think that's the only thing. There's a lot of other variables involved. Real life isn't quite so cut and dried. But yeah, that's the assumption, that there is a connection, there's a correlation between these things. Part B, analyze these data, determine whether they suggest that the instructor is an effective teacher. Okay, so the number of hours of instruction is the independent variable. And you could use either a scatter plot and there's a line of best fit. You could use the least squares method. In this case, here's a spreadsheet that was used to do this. Spreadsheets will calculate these things for you. Just to help you interpret this spreadsheet really quickly, that information was entered here, and then it plotted the graph, and it also came up with the equation of the line of best fit there. I'll come back to that. So except for an outlier at 2045, that one there, the scatter plot below indicates a strong positive linear correlation. Again, let's ignore the graph, ignore this line here, and just look at the dots. Try to just look at the dots. If you were to estimate the line of best fit, you'd think it would look something like that, right? It does look like a strong, they're very close together. It's a pretty great clumping of dots. But we got this guy, which is a problem. And, pardon me while I go all the way back. So we call that one an outlier, okay? So at first glance, it appears that the instructional hours is positively correlated to the student's test. Yeah, it looks like generally more hours means their test scores go up, except for that outlier. However, the linear regression analysis yields a line of best fit that is negative 1.133x plus about 80. So in other words, it's got an actual negative slope for the line of best fit. What does that mean? Well, that's suggesting that because of this negative slope here, that's actually saying that the more hours a student gets with the instructor, the worse they would do on their driving test, which doesn't make a lot of sense, either logically or looking at the graph. And again, it's because of the outlier, all right? But we also have a correlation coefficient of negative 0.05. Ignoring the negative, that's just because of the negative slope, that 0.05 is very, very weak. Remember, 0 means no correlation whatsoever. And again, this looks like a strong correlation. So what's going on? Well, what's going on, again, is the outlier. It's messing everything up. The outlier has a dramatic impact on this regression results because it is distant from the other data and because the sample size is quite small. There's only seven students, it looks like there. 7 people, that's a very small sample size. Although the scatter plot looked favorable, the regression analysis suggests that the instructor's lessons had no positive effects. All right, next question. Comment on any data that seems unusual. Well, again, we have an outlier, and interpreting this, maybe the person was upset today, maybe the person was sick that day, maybe it's just someone who doesn't take instruction well. Who knows what's going on? But this one student is causing the data to go way off. So in this case, it might be reasonable to exclude this data point, especially because it's such a small data set. If we had hundreds of students here, this one outlier wouldn't make much difference. But with such a small data set, it makes a big difference. So if we remove the outlier from the table and then redo it, then you can see things make more sense. You can see this line of best fit is going the way we'd expect it to. We've got a positive slope now, and we've got a much stronger correlation. That's R squared. So if you take the square root of that, you'll get the actual R value. The R value is 0.93. So the results suggest that the instructor may be an effective teacher overall. To do a proper evaluation, you need a larger set of data. Always want more data, right? More information about the outlier, or ideally both.